As Earth's climate changes, one of the hardest things to figure out is exactly how the planet will change in response, like how weather patterns will shift and how species may or may not adapt. And while we can't know the future for sure, we can get a lot of good clues from the past. Our planet has been through a lot of changes, and understanding different chapters in its history can help us figure out what might be coming. But most of those changes took place before anyone was around to record them, so it takes some serious detective work to figure out what the world was like back then. Fortunately, scientists have some pretty cool tools that help them reconstruct the climate in the past. One place scientists can look for clues is in a common mineral called calcium carbonate, which forms in lots of places and is especially common in the ocean. It's made of, well, calcium and carbonate ions, and if conditions are right, this mineral can come together all by itself. Crystals just form straight out of the water. But more often, it's marine organisms that harvest calcium and carbonate ions and turn them into shells and skeletons. And without knowing it, these little organisms are also recording small snapshots of Earth's history. That's because nature is messy. So when calcium carbonate forms, it's rarely ever pure. It contains other elements from the environment that get locked up in its crystal structure. These impurities are called trace elements, and what makes them good snapshots of the past is the fact that they don't always appear in the same quantities. Depending on different conditions in the environment, you'll get larger or smaller numbers of impurities in the mineral. For example, scientists can see that easily in a species of zooplankton called foraminifera, which have shells made of calcium carbonate. Many of these microscopic organisms live near the surface of the ocean, where the water temperature is closely tied to the temperature of the air. And scientists have observed that at times when temperatures were higher on Earth, foraminifera had a lot more magnesium in their shells. We don't know exactly why that's the case, but it may be because at higher temperatures, the motion of the molecules becomes more energetic, and that could make it easier for magnesium to take the place of calcium in the crystal lattice. Regardless of how it works, many experiments have shown that this relationship between the amount of magnesium in foraminifera and the Earth's temperature is extremely consistent across time. This means that scientists can take fossilized shells, whose age they already know, measure how much magnesium is in them, and estimate the local temperature at that time. Scientists can also get similar information from corals, which make their skeletons out of calcium carbonate too. In corals, calcium carbonate has a different mineral structure, so it's not the right shape to capture magnesium, but it does capture the element strontium, and the amount of strontium is also related to temperature. Except, strontium actually has the opposite relationship to temperature. As temperatures go up, the amount of strontium in coral shells decreases. Like magnesium in foraminifera, this relationship isn't exactly understood. But experiments have found that it's consistent, so it can be used to estimate temperatures in the past. This is extremely useful, because both foraminifera and corals can be found all over the world. There are other ways of extracting temperature information from certain places, like scientists can study ice cores to learn about temperature changes at the poles, but nothing as wide-ranging as the clues in calcium carbonate. When it comes to piecing together climate history on land, scientists typically have to resort to a different set of clues. You might have heard of scientists using the width of tree rings as a way to figure out what environmental conditions were like in the past, but trees aren't the only things that accumulate layers of climate clues. In caves, mineral deposits known as speleothems do sort of a similar thing. You probably know of speleothems by their more common names, stalactites and stalagmites. These, along with flat slabs on the cave floor known as flowstones, are the three main types of mineral deposits in caves. They form when running or dripping water travels through a cave system. And actually, just like foraminifera shells, they're often made of calcium carbonate, or some other mineral containing calcium. That's because water becomes slightly acidic as it picks up carbon dioxide in soil. As a result, it dissolves some of the calcium out of the limestone rock it passes through. Once it gets to the cave, the water deposits some of that calcium in a mineral form. These mineral deposits can build up over hundreds of thousands or even millions of years, and each layer says something about what the rainfall was like the year it formed. This is because the hydrogen and oxygen atoms that make up water have different isotopes, meaning some of the atoms have an extra neutron or two. Those extra neutrons don't affect an atom's charge or anything, but they do change its weight. So atoms with extra neutrons are known as heavy isotopes. And although they're pretty rare, when a cloud gets to its breaking point and is ready to lose some water, the first raindrops that fall are usually made of heavy isotopes. But during periods of heavy rainfall, where clouds empty out more and more water, the number of heavy isotopes gets depleted early on, and the rain contains more of those light isotopes that were originally left behind. Since speleothems form from rainwater, you can measure the ratio of heavy oxygen isotopes to light ones and estimate how much it rained during a certain time. time. In years with heavier rain, you'll get more light isotopes. This makes speleothems great tools to study events like monsoons, and they also make it possible to connect changes in climate to local weather. Even better, since they form in caves, these features are naturally protected from erosion, so they stick around for a long time. Caves are generally great places to look for old climate clues because of how they're protected from erosion, and they're often home to one particular climate-recording creature: the bat. Like corals or foraminifera, bats are natural historians, but rather than capture climate information in their skeletons, bats leave behind clues in their poop. They deposit their poop, known as guano, in the caves where they live, and over time, it preserves information about conditions in the past. Even better, bats tend to poop in the same place for thousands of years, so piles of bat poop are like history books full of old climate details. By analyzing old samples of bat guano, scientists can measure the levels of different elements, which can be clues to events happening at that time. Bat guano is often used for figuring out what humans were up to in the past. Like, scientists were able to connect a spike in nitrogen to the introduction of manure-based fertilizer in Jamaica around 3000 BCE. They've also seen the Industrial Revolution in bat guano, which shows up as an increase in lead levels around 1760. That's because these environmental changes altered the content of the things the bats ate and pooped. But in addition to revealing human history, bat guano also offers clues about climate history. For example, the levels of carbon and hydrogen isotopes can offer clues about rainfall. In a 2008 study, scientists used bat guano from the Grand Canyon to reconstruct the history of monsoons in the region over 20,000 years. Carbon isotopes can also tell you something about the types of plants in the area. For instance, thanks to bat guano, scientists figured out that some of today's tropical forests in the Philippines used to be covered in dry savannas. Guano can be really valuable in low-lying areas or tropical regions where sediment layers aren't as well preserved as they are elsewhere. Unfortunately, over time, guano has been harvested as a fertilizer, so most prehistoric guano deposits have disappeared. But some still exist in remote parts of the world where deposits could be up to hundreds of thousands of years old, and they may have a lot to tell us about how our planet has changed. Water is really closely tied to climate, but since it's always moving or evaporating, we usually can't just study a body of water from the past. Except when we can. There are places on the planet where prehistoric water has been preserved over time. And it's all thanks to the mineral gypsum. Gypsum is one of the softest minerals on the planet, meaning you can very easily break it or rub a piece off. And that's partly because of how hydrated it is. Water is naturally a part of gypsum's crystal structure. And as gypsum forms, water from the environment gets trapped in the mineral. Essentially, the water becomes fossilized. And what's even more amazing is by analyzing gypsum, scientists can measure the chemistry of actual water samples from Earth's past. That actually has to do with the water's light and heavy isotopes again. Since it's easier to lift lighter isotopes than heavier ones, lighter isotopes tend to evaporate first. So during times of drought, when bodies of water are drying up, the ratio of light to heavy isotopes changes. All of that information gets trapped in gypsum, and that means scientists can use old gypsum to measure the severity of droughts in the past. In fact, in research published in 2018, scientists analyzed gypsum from around the time when the Mayan civilization collapsed around the year 900 CE, and linked that historical event with an extreme extended drought. Like, we can actually measure the drought that happened near the end of the Mayan civilization, which is pretty incredible. And since evaporation rates are tied to temperature, scientists have also been able to use the clues in gypsum to track warmer and cooler periods over land in the past. A lot of climate reconstruction relies on information about water, not just water on the ground, but also moisture in the air. And to figure out what atmospheric moisture was like in the past, scientists can look at fossilized leaves. Leaves record climate data every hour of every day, and they store it in their lipids, which are fatty acids made up of long chains of carbon and hydrogen atoms. Lipids can have different lengths, and one thing that can affect their length is stress. For instance, when the air is drier, plants produce extra long lipids to alter the chemistry of their leaf wax, that protective outer coating, and that keeps them from losing precious water to the air. So by looking at fossilized leaves, scientists can measure the length of lipid chains and leaf waxes, and connect differences in length to differences in atmospheric moisture. That's a super helpful detail to have when you're trying to reconstruct a climate that existed in the past, because atmospheric moisture offers a lot of clues about weather patterns. For instance, rain is more likely to occur in places with high humidity, and when the air is dry for long periods of time, it can sometimes be a sign of drought. So just by looking at atmospheric moisture, we can start to figure out past weather patterns all over the world. None of these tools is perfect, but altogether, they can help scientists piece together Earth's climate history, and it's kind of amazing how much they can tell us. As we decipher clues to Earth's temperature, humidity, and rainfall at different points in its past, we can come up with a clearer picture of what the planet used to be like, and that'll give us a better shot at envisioning and preparing for the future. Thanks for watching this episode of SciShow. And to see what scientists have been able to do with clues like these, check out our episode on the history of Earth's climate.